Hello and welcome to yet another video of Cornerstones of Math. Today I am going to solve the following problems. As for problem A, consider a region enclosed by graphs of y equals sine x, x equals a, x equals b, and the x-axis. The graph of x equals c divides this region into two regions of equal area. Then express c in terms of a and b. In problems B and C are the same as problem A, with only the curves are different. In problem B, the curve is y equals tangent x, and in problem C, the curve is y equals secant x tangent x. If you're wondering why I chose this strange function for the third problem, perhaps you'll get it if you watch till the end. So the first problem, for the curve y equals sine x. We can set up the equation as follows. The area on the left can be expressed as the integral of sine x from a to c, and this must equal the area on the right, which is the integral of sine x from c to b. Since the antiderivative of sine x is minus cosine x, we have a and c here, and minus cosine x with c and b here. So minus cosine c plus cosine a equals minus cosine b plus cosine c. This gives cosine c equals cosine a plus cosine b divided by 2. Therefore, we have c equals inverse cosine of cosine a plus cosine b over 2. Now the second one with the graph of y equals tangent x. The integral relation is pretty much the same, just with different integrand. So we have the integral of tangent x from a to c is equal to the integral of tangent x from c to b. In case you're unfamiliar with the antiderivative of tangent x is equal to sine x over cosine x. Then we put a minus sign on the numerator and a minus sign at the front. In this way, the numerator becomes the derivative of the denominator, and we have seen this behavior in the derivatives of logarithmic functions. More specifically, this is the derivative of ln absolute value of cosine x. So we have minus ln cosine x plus c as antiderivative. Therefore, we have minus ln absolute cosine x with a and c, and minus ln absolute value of cosine x with c and b. Due to the range for a and b given in this problem, we don't need absolute value notation here. So we have minus ln cosine c plus ln cosine a equals minus ln cosine b plus ln cosine c. Now if we solve for ln cosine c, we obtain ln cosine a plus ln cosine b over 2. If we combine two logarithms, we can write this as 1/2 times ln cosine a cosine b, which is equal to ln positive square root of cosine a cosine b, because in this problem we know for sure that this is positive. This gives cosine c equals square root of cosine a cosine b. Therefore, c equals inverse cosine of square root of cosine a cosine b. And the final one with the graph of secant x tangent x. So first we write integral of secant x tangent x from a to c equals integral of secant x tangent x from c to b. And I think many of you are already familiar with this function secant x tangent x. It is the derivative of secant x. So the antiderivative of secant x tangent x is just secant x. So we have secant x and secant x. So secant c minus secant a equals secant b minus secant c, which gives secant c equals secant a plus secant b over 2. Here you can just take inverse and write c using inverse secant function, but just for fun, let us change everything into cosine functions in order to keep things consistent with previous two problems. So we have 1 over cosine c equals 1/2 times 1 over cosine a plus 1 over cosine b, which is equal to cosine a plus cosine b divided by 2 cosine a cosine b. So we have cosine c equals 2 cosine a cosine b divided by cosine a plus cosine b, which gives c equals inverse cosine of 2 cosine a cosine b divided by cosine a plus cosine b. And that's all for today's video. Thank you all for watching. Please don't forget to hit the like and subscribe buttons if you enjoyed this video, and I will see you in another video.